Okay, apparently we're recording.
Girl, these are on file. I know.
Okay.
I cried.
Mistake. So I'm
Call that a blessing.
so I'm trying something new, and hopefully I'll remember to do it every time. Is it like right before class starts, or maybe when class starts and people are not here yet, or certain people? I let's put up an outline of what is tentatively in store. Do not hold me to this rigidly. So it's to be understood that there's always room for a tangent in here, but this is at least what I plan to cover going in. Last time we talked about certain kind of special kind of linear system involving a banded matrix. So now we're going to look at other kinds. Glad you could join us. Please move faster next time. One of you is missing. Okay, all right. Okay. Okay. So now, okay. So now we're going to look at a case where a matrix is symmetric. We're only going to spend a little time on that. What we really care about today is, or what I care about and will cause you to care about, is if the matrix is not only symmetric, but what is called positive definite. So I'll define what all those terms mean. And now you know about the LU decomposition that's involved in the homework, which I hope that you're making good progress on because it's kind of due today. And yes, kind of do. And the LU decomposition is also known as the LU factorization. I just chose to use the term decomposition because it seems like most people call it that. But there are two other factorizations or decompositions that we're going to learn about today that are closely related to LU. The LDLT factorization and then the Cholesky factorization. Well, LDLT seems like a drug or something. like instead of getting busted for LSD or PCP, it's like, here, have some LDLT.
I mean, it's good, right?
Yeah. Okay. But before I get into talking about symmetric or positive definite systems, I need to tell you about how I screwed up. Little screw-ups on the for homework 2. So one of the problems involving forward substitution, and that is okay. So 3.2.9, where I give the specification for the function. It should be y is equal to forward sub LV. I had LY, so I'll have to fix that. Now, the way forward substitution algorithm is laid out, you could think of it as like overwriting the input with the output, so it could be done that way, but I didn't want to like force that. So, because we're solving a system, L times Y is equal to B. Okay, so, and the other item was in the 3.2.20 hints. So not the problem itself, but in the hints document I put up, because it's a big help that turned out to be. It should be, when looking for the largest element in part of a column, it should be A, J down to N, column J. I had somehow put an N in that last position. So it's important that, like for that problem, which is most significant coding-wise, of at least you're piggybacking off of earlier functions, to write a routine to solve Ax equals B, be sure to test these things. So if you make up a random matrix A, like in a random vector B, and you go ahead and solve Ax equals B, so of compatible sizes, like for instance a 5x5 matrix A and a 5x1 vector B. So you can check, like solve it using MATLAB's routine, so just using the backslash. So that should agree with what happens using your function, solving xb with the same a and b. So don't turn it in unless you've done that, please. The thing is, if you go ahead and do that and include that in your diary and send me the diary, then I can see, oh, your code works. I'm going to look at it anyway to make sure that no one's trying to pull a fast one on me. But it speeds, it moves along with the grading process. Okay. I've gotten homework 1 grades back to almost everyone. Those who have not, I just got scatterbrained, so I'll take care of the rest in short order. But all of them look great, so that's what matters. Okay, and similar comment applies to the other functions like forward substitution, backward substitution, because if you get those working, then that just makes it much easier to ensure that solve AXB works. So for instance, if forward and back substitution work, but solve AXB doesn't, then you know that something went wrong with your Gaussian elimination, for instance. Okay. Well, I have one problem where I give you a matrix, and you need to compute the LU decomposition by hand. So once you have your L and your U from that, go ahead and type them into MATLAB, multiply them. Make sure you recover the original A. So that way you can make sure that you did that right. Okay. All right. I know what the response to this is going to be based on history, but I feel obligated to ask anyway. Are there any pressing homework questions? I just never ask that again. Okay.
Always ask.
Okay. Because I know the first time I don't, somebody would be like, hey,
Someone's
he's not
gonna have
helping us
a
with homework. And
Mhm.
yeah. So.
Well, that's what email was created for.
But people aren't using that either.
Well, I use that.
Well, exception. Yeah. And there are a few other exceptions, but the point is there's still exceptions. So maybe I'm making homework too easy. Well. Okay. So predictable. Okay. All right. Okay, so that's all we say for now about
Well, I do have one
Yeah.
question. As
Yeah.
far as testing,
Yeah.
there are other ways to test, like A times X should equal B.
Yeah, you can always do that too.
That's what I did with my testing. So
Oh yeah,
already
that would work.
submitted. Okay, so
Okay, yeah.
if I need to redo it, I'm more than happy to redo a testing. That's a really easy thing to redo.
Well, so what you're doing in that case is when you're checking the agreement of B with A times X, is you're making sure the residual is small. So it is an important term for us later on. B, I'll call it R for residual, is equal to B minus AX. So ideally that should be 0. And what you're seeing is, I guess is that what you did, like B minus AX, and made sure it was 0?
Yes,
Okay. Yeah. Although what we will see, oh wait, I didn't cover that. Dang it. Okay, it's in the book. Everything's in the book. That there are situations where the residual may be small, but the error, the difference between the exact solution and your computer solution, might still be large. That's about conditioning. That if I let okay, so if I do x hat, we'll call x hat the computed solution by whatever means that has any kind of error, like round off error or whatever error you introduce into it. And to plain old x, I refer to the exact solution. So that's residual, that ideally should be 0. As opposed to the error, which we'll call E, which would be the exact solution minus the approximate. Now that is what you want to actually be small. Now you could think of this as, well, it kind of is like a forward error, backward error relationship, those of you who took last semester's class. And it turns out that now for the exact solution, both would be 0. But in general, the magnitude of the error, so if I use a vector norm, we can say that is less than or equal to, actually the relative error is less than or equal to the condition number of A times the norm of residual relative to the norm of B. So what that means is, if A is ill-conditioned, the norm of residual could be very small, the norm of the error could still be very large. So have to be careful about that. But for this assignment, especially generating a random case, yes, testing residual is perfectly fine. And see, that's why I told you, I gave you my disclaimer about tangents, because that has nothing to do with today's material. But still, very important numerical linear algebra fun fact there, or actually could be a not so fun fact. Okay, so now I'll spend the rest of the time talking about symmetric matrices and subclasses thereof. Let's see, and please tell me we're still recording. Yes. Oh, wow, we're up to almost a gig already. How much time have I wasted? Sheesh. Okay. Be like the biggest video file ever. Okay. Now, some basic terms I need to define, because I haven't used them before. So I have any matrix A. So the with the superscript T is the transpose of A, and that's defined by reversing the signs of the rows and columns. So another thing I'm trying to do, this is to offer benefit for your notes, boxing important things. So the ij entry of a transpose is just a ji. So you're just swapping the indices. And this is true for any kind of matrix. It doesn't have to be a square matrix. So for example, if I make up say a 3 by 2 matrix, so then A transpose is a 2 by 3 matrix. So first row of A is the first column of A transpose. Now, so what if a matrix is equal to its own transpose? Okay, so A is symmetric, and in this case it has to be square for it to even make sense. If A is equal to its own transpose. So an example of that would be, so it doesn't really matter what to put on a diagonal, but the off-diagonal entries have to be like mirror images of each other. So if I draw a line down the diagonal, you can see that the matrix, there's like a mirror image thing going on here. So that's how you can spot a symmetric matrix. Okay. What I should throw in here, as long as I'm talking about the transpose properties, of a transpose. You never know when these might be needed. Okay. First, if you take the transpose of the transpose, that just brings you back to the original matrix, because you're reversing rows and columns, and then you're reversing them again. Second, if a matrix is non-singular, so invertible, the inverse of a transpose is equal to the transpose of the inverse. So if you take a matrix, you take its transpose or its inverse, or you do both items, it doesn't matter what order in which you do them. which is convenient. And for that reason, a symbol they make for that is this A to minus T. So it's A inverse transpose. So that way you're not having to write parentheses. It reduces clutter. Let's see, let's make a little more room here. The transpose of a sum is the sum of the transposes, so that works out quite straightforwardly. And finally, the transpose of a product is a product of transposes, but, very important, in reverse order. Okay. Actually, similar property applies to the inverse. The inverse of a product of the inverse is in reverse order. Anyone who is taking modern algebra right now needs to keep that in mind because it comes up all the time in there. So, unless you're dealing like with an abelian group, so beware. Okay, so hopefully I saved you a few lost points. Okay. Now, so what happens when we're solving system AX equals B, and now we know the matrix is symmetric? How does that affect things? Okay. So what I'm going to do is I'm going to change the LU decomposition a little bit. Now, for the time being, we're not going to deal with pivoting. Pivoting just messes things up. So I have A is equal to LU. So we're going to assume that LU decomposition exists, which again is not always true. But I'm going to write it a little differently. LDM transpose. So what I'm doing with D, the matrix D it's called D because it's a diagonal matrix. And I just put the diagonal entries of U on the diagonal. Everything else is 0. And then M transpose, all that is equal to D inverse times U. So that way, if I put this in here, I have LD D inverse U, but D and the D inverse cancel out, and you're back to LU. Now, what happens here is, this is a matrix that will have 1s on the diagonal. 0's down here, because U is upper triangular, D inverse is diagonal, so the whole product is still going to be upper triangular. And then I'll have stuff up here I don't really care about. Okay. So, how can we describe a matrix like this? We have various types of matrices that we've seen. What would we call this one? Like in terms of its structure, where it's
Upper triangular.
and what more can we say? Unit, upper triangular. But that's M transpose. So really, what that means is M is unit lower triangular. So all I've done here is I've factored out U. I've factored U as a product of a diagonal matrix where the diagonal entries go, and then a unit upper triangular matrix, which is a transpose of a unit lower triangular matrix. So now L and M are both unit lower triangular. So this is called the LDMT factorization. Now, this is actually kind of useless for a general matrix because DM transpose, that's just U. So it doesn't really give you anything with solving systems. But when the matrix A is symmetric, that's when things get more interesting. So let's let A, so this is the LDMT factorization. Barely worth spending time on. In fact, it's barely worth mentioning. I know, so maligned. But hey, got some ink and gall with Van Loan, so whatever. so it lives on. So let A equal A transpose. So now I can apply that to this factorization. So I have LDM transpose is equal to its own transpose. Okay. And if I apply the fourth property there, the transpose of a product is a product of a transpose is in reverse order. So that would be M transpose transpose, which by the first property is just M. And then D transpose, but D is a diagonal matrix. A diagonal matrix is already symmetric, so it's just D. And then I have L transpose. So now I have this equality for the, oh, whoops, totally blew it there. Well, okay, not so bad. For the symmetric case. Now, L and M are both unit lower triangular. Now, what do we know about a unit lower triangular matrix? This actually came up in the second homework, which hopefully you've done this problem. What property does a unit lower triangular matrix have because of its diagonal entries being 1?
It's determinant.
Sorry, what?
Determinant equals 1.
Yeah, determinant equals 1. So therefore, it is non-singular. It is invertible.
Yes.
So I can work with the inverses of both M and L. So I can multiply, like for instance, I'll multiply both sides by L inverse. So it cancels on the left side, and then I have L inverse M. All right, and then what I'll do is I'll multiply on the right by L inverse transpose. Okay, but using the properties of a transpose. The product of transposes is the transpose of a product in reverse order. So I have D L inverse M, whole thing transpose, is equal to L inverse M D. Okay. Now, so notice we have the same matrix in parentheses, it's just that one is transposed and the other is not. Now, keeping in mind that L and M are unit lower triangular. And what it means when you take the inverse or a product of lower triangular matrices. Again, from the homework, you proved that. Or you better have by tonight. Can anyone tell me what is the triangularity of the right side? The diagonal matrix won't affect anything. So right side, lower or upper triangular? Anyone? Yes. L and M are lower, and therefore M inverse, L inverse is lower. D won't affect anything because it's lower and upper. So yeah, this is lower triangular. Right side. Look at what's different. Therefore, it is upper. Yeah, but to transpose a lower triangular matrix, you get an upper triangular matrix. So this right here is upper triangular. If a lower triangular and upper triangular matrix are equal, what can you say about them?
They are diagonal.
Yeah, they have to both. So if they're equal, that means both are lower triangular and both are upper triangular. And a matrix that is both upper and lower triangular is
A diagonal,
diagonal matrix. Yeah, so both are diagonal. Now D is already diagonal. Therefore, L inverse M is diagonal. I've run out of room. Dang it. Okay. Okay. So in other words, L inverse M is diagonal. But knowing what we know about L and M, their structure, what are the diagonal entries of L and M? Yeah, they both have diagonal entries that are equal to 1. that means that their product has to also, because you take lower triangular matrices,
Okay, yes.
you multiply them, their diagonal entries are just a product of the diagonal entries of the original.
Yeah,
So L inverse M is equal to the identity. And I can rearrange this. That means that M equals L. So, so then A, if it's symmetric, has a LDLT or LDL transpose factorization. Okay. All right. So L is unit lower triangular. Recall my shorthand for that, and then D is a diagonal matrix. So if your matrix is symmetric, you can go ahead and compute this instead of LU. And the reason why this is helpful now, whereas LDMT it's like whatever, is because these are the same. So that's one less thing to compute. You don't even have to compute U really at all, because you do need D, but D is a diagonal matrix. So what you can do is use a process that's similar to Gaussian elimination. And I'm not giving problems on LDLT, but it's a pathway to the next factorization, which I did give you problems on. So that's why I'm covering it. So as a result, so to compute this, it requires roughly 1/3 n cubed flops or floating point operations or arithmetic operations. Now, okay, I want to make sure it's still recording.
It's blinking weird.
Yeah. Okay. And if it's still racking up space. Okay, yep, that helps. All right, we're good. Okay, now, can anyone tell me how this compares to the amount of work required for plain old Gaussian elimination?
Wasn't it 4/3 or something? 2/3?
Yeah, it's
2/3. Yeah, so you cut the work down by half. Okay. Now, once you have it, the way you solve a system of equations is very similar to with LU. You do forward substitution, then you do n divisions. That was like one of the homework 1 problems. And then L transpose is upper triangular, so that's back substitution. So that whole process is pretty much the same. Okay, so the bottom line is a symmetric matrix. You can solve a system using roughly half the arithmetic operations in for a general system. So it's important to take advantage of that symmetry. All right, and so there is a MATLAB function that's called LDL that computes the LDLT factorization. Now, I will say a quick word about pivoting. One complication for pivoting is that you want to preserve symmetry. If you swap rows of a matrix that is symmetric, it's no longer symmetric. So the way that is handled is, if you're going to swap, you swap both rows and columns. So it's kind of like almost. Now, you can do partial pivoting, but once you decide what rows to swap, go ahead and swap the corresponding columns, and then symmetry is preserved. And you still get the benefit of partial pivoting. Okay, so now when you have the thing I want to bring up here is, okay, I guess my bottom line. Because A is symmetric, its decomposition, whatever decomposition you use, should also have symmetry, which LU does not have. You have this unit lower triangular matrix and upper triangular matrix. There's no symmetry between them, but LDLT does. So to reduce the computational cost, and it makes so what you have is, because you have half the entries, because half of the entries are mirrored by the other half, that leads to half the cost. So 1/3 n cubed instead of 2/3 n cubed for the counterpart of Gaussian elimination. Okay. All right. That's definitely worth boxing. Okay. Any questions to this point? Yeah.
I do have one question. You mentioned swapping if you're going to pivot, swap the rows, then swap the columns, but you didn't say complete pivoting.
Right.
I'm missing something there. Why
Okay,
is that not
because
complete pivoting?
You are not obligated to search for the largest element in that entire remaining portion of a matrix. You can still search for the largest element in a portion of a column like you do in partial pivoting. So in terms of how you choose, then, because also if you're doing complete pivoting, so that's where you're swapping rows and columns, those are not guaranteed to be symmetric choices.
No.
Because who knows where that largest entry is going to be. So actually complete pivoting as described may not be the best idea. Maybe you compromise and find an entry that is the largest that will result in a symmetric row and column swap.
Yeah.
And that would work. Okay, well, let's see. So for instance, if you're okay, yeah, because you're trying to find. You know what? Really, what you're doing is that would require you to look for entries along the diagonal only, because say you're trying to find an entry to swap with entry 3, 3.
Yeah.
And you want to swap row and column 3 with row and column something else.
Yeah.
Those have to agree. So in fact, you're still not incurring overhead as far as comparisons.
Yeah.
It's still order n squared comparisons like partial pivoting. So.
Now, would it be fair to describe that as doing a partial pivoting of, say, either an upper or lower triangular matrix, and then concatenating it with its transpose, half the pivot piece?
Okay.
You take just the upper triangular elements of, say, a symmetric matrix, conduct partial pivoting, and then concatenate it with the transpose. So I hate to use U. Let's call this. Let's say the upper elements are V. So pivoting times V, and then concatenate it with the transpose.
Well, so what's happening is, you're trying to, you think it's reducing A to not just upper triangular form, but to diagonal form. So you start with A, you perform a permutation swap rows, then swap columns.
Okay.
Then do a row operation, and do the corresponding column operation, and you keep going until eventually the result is a diagonal matrix.
Okay. Yes.
Yeah.
Okay.
Okay, that's not how the LDLT algorithm actually works.
No,
although it could. Yeah. Okay. All right. So now, during the rest of the time, we'll talk about a subclass of symmetric matrices that are of particular interest. Of course, now that I've been talking totally improv about pivoting with symmetric matrices, I hope I didn't say something that's completely wrong. But
it's all right. I guarantee it.
Okay. All right.
Guarantee it might not be worth much, but
okay. Well, I was thinking like, if you swap, for instance, for example, rows 2 and 5,
Okay.
and then you swap columns 2 and 5. So, for instance, the 5-5 entry would be located 2-2. So in fact, by doing partial pivoting, if you think of it from a partial pivoting point of view or a complete pivoting point of view, the effect is the same. You're only looking along a diagonal from the largest one. Yeah. Okay. At least in my head. So for anyone watching that's in the American analysis community, I've not really thought this through. So don't judge. I'm a spectrum methods person. What do you want? Okay.
So no hate mail in the comments.
Right. But who's watching anyway? But still.
That will be the video that goes viral.
Yeah. Okay. Okay. Now, let's see. So, the idea is, you take something as ordinary and innocuous as a positive number, and now we want to generalize the overly simple concept of a positive number to a matrix, like the notion of a matrix being positive. But a matrix has, n squared entries for n by n matrix. So how can we describe it as being positive? And you might think, well, what would make a matrix positive? Well, maybe all the entries have to be positive. But actually, that doesn't work at all. In fact, I can easily come up with an example that fails horribly. Because if we consider ax equals b, where n is equal to 1, so trivial linear equation, ax equals b. Now, and we'll assume that a is greater than 0. So in that case, of course, the system is solvable. So you can solve for x and get b over a. So if you're trying to think what would make a matrix positive in some sense, I'll set n equal 2, and I'll consider A equal to a matrix that has positive entries. Okay, but then I'll make up a vector B, which is let's see, 1, 1. Now, based on this matrix A, can anyone tell me why I cannot solve this system?
Pretty the same.
What's the same?
No.
Okay. What's wrong with A? Yeah, A is a singular matrix. If you take the determinant of this, A times 2 is 16, minus 4 times 4 is 16. The determinant of A is 0. So it's definitely not enough to have a matrix of positive entries to be considered as a generalization of a positive number. Maybe you could argue that the determinant of A has to be positive. That's perfectly reasonable. But that can also, but that isn't going to go far enough. You could argue maybe A should have positive eigenvalues. That actually is enough. And I could use that as a definition, but the definition typically given is this. a symmetric positive definite if, well, of course, A has to equal A transpose for it to be symmetric. But the positive definite part is X transpose AX must be strictly positive for any non-zero vector X. Okay. This expression here is an example of what is called a quadratic form. Because you have the same vector on the left and the right. Now, for instance, if n equals 1, this just reduces to ax squared. And for that to be positive, a should be a positive number. So this is the generalization of the notion of a positive number to an n by n matrix. Now, what's interesting is there's actually some disagreement among numerical analysis textbooks about whether a positive definite matrix also has to be symmetric. So, like for instance, I found Galvin van Loon does not require that you can call a matrix positive definite if this is true, whether it's symmetric or not. But other books will say, no, you don't call it this unless it's also symmetric. And that's what I'm siding with. So I guess now I have a book, so I have a dog in the fight.
You got a dog in the fight.
So, yeah. So we need to have both of these together to call a matrix symmetric positive definite. Okay. Now, so here's some properties of actually a convenient abbreviation is it's inconvenient to write out symmetric positive definite all the time. So we call them SPD for symmetric positive definite. So properties of SPD matrices. Okay. So first, the determinant is positive. So that means that A is definitely non-singular or invertible. Actually, I give a homework problem. This is for the next homework. That if A is SPD, show that its inverse is also SPD. So that means for a homework problem, you cannot say, "Oh, because Dr. Lambert said so in class." It's not hard to prove, though. Yes, even for a student.
A inverse exists.
And yeah, that's meant to be an ampersand.
Sorry.
Okay. Second, all eigenvalues of A are strictly positive, which actually is related to the first statement because the determinant is a product of all the eigenvalues, so we would need that to be true. Okay. All of the diagonal entries are positive. Now, you are allowed to have negative off-diagonal entries. There's no problem with that. It's just that the diagonal ones must be positive. And the largest entry of A anywhere in a matrix has to be on a diagonal. We wouldn't say that the matrix is diagonally dominant necessarily, but you generally want to have your diagonal entries larger than your off-diagonal ones to ensure positive definiteness. Okay. And I want to make sure that I'm not forgetting any more properties. Probably not, but Okay. Okay. Now, this condition right here, or even this condition, they can be used to quickly determine that a matrix is not SPD. But in general, you can't. If you have a matrix that is larger than a 2x2, you really can't tell if a matrix is SPD, a symmetric matrix is SPD, just by looking at it. And it's actually it's not easy to check. But I can give you conditions that can be checked to be absolutely certain that it's SPD. However, if it's practical to check this way, it's another matter. All right. So if given an A is symmetric, I just realized that I got confused when I was in the middle of writing this because, I'm about to write symmetric matrix A, but why have I already written A? Well, that's not the matrix A. That's just the article A. There's an A and a the. So, whoops. So if a given matrix is symmetric, how do we know that it's also positive definite? Because the definition that I gave is not something that's easily checked, making sure that X transpose AX is positive for all the infinitely many vectors, non-zero vectors X that are out there. So here's what we can say, that so it is positive definite. Okay, well, I'm going to use a box here and make it a statement self-contained. So asymmetric. It's also positive definite if and only if the determinant of these matrices, which I'm about to define, A sub k, are positive for k equal 1 to n, where ak is just the upper left k by k block of A. So you're just taking the first k rows and columns. Okay. And these are called the leading principal submatrices of A. And these determinants are called the minors, the leading principal minors of A. So if A has all positive leading principal minors, or in other words, all the leading principal submatrices have positive determinants, then you can say A is symmetric positive definite. But computing determinants is quite expensive. Well, it takes at least order n cubed operations, so that's kind of unfortunate. Okay. But there's one nice thing about this fun fact. If you know that a matrix is symmetric positive definite, the consequences for solving AX equals B with a symmetric positive definite matrix, because these leading principal submatrices, we've actually seen these before. With regard to the LU decomposition, that turns out A has an LU decomposition if and only if these have non-zero determinants. But if it's symmetric and they're also positive, then it's SPD. So what we can conclude from this that if A is SPD, the LU decomposition is guaranteed to exist. In other words, you are never required to pivot during Gaussian elimination. So that's one nice thing, because with symmetric matrices, if you're computing LDLT, you may need to pivot, like to avoid division by 0. That will never ever happen with a SPD matrix. Now, pivoting might still be a good idea to reduce propagation of round-off error, but it's not something that you're ever going to be in a real bind where you must. Like I said, symmetric positive definite matrix can definitely be as ill-conditioned as any other. Okay. Now, but this is inefficient. This takes 2/3 n-cubed operations. Now we could do the LDLT factorization, but there's another factorization that's a little bit simpler. We use the Cholesky factorization. A is equal to GG transpose, where G is lower triangular. So we still have a lower triangular times an upper triangular matrix, just like in the LU decomposition. The difference is now we're requiring these two matrices in the factorization to be transposes of each other. And we also require that each diagonal entry be positive. They're going to be zero, or not going to be non-zero anyway. But by requiring positive, we ensure that it's unique. Okay. All right. So this factorization, like LDLT, requires half floating point operations as LU.
Those are G's, right?
Yes, those are uppercase G's.
You say so.
As opposed to what?
I have no idea.
Okay.
So, it's like,
Some
that's a
freaky
new
Greek
symbol.
letter that you've never seen before? Or?
Yeah.
Okay.
It's thoroughly.
So this is the same complexity as LDLT. And in fact, LDLT and Cholesky are closely related. So if A is equal to LDL transpose, and it's also equal to GG transpose, we can actually say that G is equal to LD to the 1/2. Because for a symmetric positive definite matrix, the elements of diagonal entries of D must be positive. So we can take the positive square root. So in fact, this is why LDLT is known as square root free Cholesky. Because the process of computing a Cholesky factorization does require, unfortunately, square roots. Okay. So what I'm going to try to show you, hopefully can fit it in time, is just a simple example of how the Cholesky factorization can be computed directly from this equation, A equals GG transpose. You can figure out how it goes, and then from there the algorithm will emerge. So the algorithm is given in the text, and that's what you'll use to implement it for homework 3. But this way I can give you an idea as to how the algorithm comes about. Okay. So if I have a 3x3 symmetric positive definite matrix A, and what I'm going to do is I'm going to write the superdiagonal entries. You could say wrong, but not really because it's symmetric. So normally I would write A12 here, but I'm going to write A21 because these are supposed to be equal anyway. So reducing the number of distinct entries that we work with. Okay. All right. Now, this is supposed to equal GG transpose. So I'll go ahead and write out GG transpose. Where G is lower triangular. So that'd be G11, G22, G33, and then the lower triangle, I fill that in too. Okay, and then it's transpose over here. And I'll index the same way because I'm just transposing G. Okay. So what you could do is, on the right side, just go ahead and carry out the product. Multiply these matrices, and we'll look at them entry by entry. So A11 would be equal to the 1-1 entry of this. So you would go across the first row and down the first column, multiply them. So what do you get? For the 1-1 entry. G11 squared. So we know what G11 is. It's the square root of A11. Now let's look at the 2-1 entry. So I go across the first row, down the same first column. So A21, what would that be equal to?
G21 times G11.
Yeah, and we know what G11 is, so we can get G21.
Yeah.
So G21 is equal to A21 over G11. And then the 3-1 entry will work out the same way. So A31 is G31, G11. So that means that G31 is A31 over G11. Okay. All right, so now we figured out the first column of G. Now to get the second column, we just need G22 and G32, so we're going to focus on the 2-2 entries. So now I go across the second row, down the second column. So the expressions get a little more complicated this time. So what is A22?
That should be
So second row, second column.
G21 squared plus G22 squared?
Yeah. So the diagonal entries of A will always be equal to a sum of squares of entries of G. Now we know what G21 is, so we can solve for G22. That will again involve a square root. That'll be A22, but we have to subtract off G21 squared first. And here we see where if A is not symmetric positive definite, and we foolhardily try this anyway, this is one place where it can go wrong. We might end up taking the square root of a negative number. Here's where something can go wrong. If we get exactly 0 here, then we're dividing by 0 later. So this may be actually not just a good way to compute this factorization, but also determine if A is symmetric positive definite in the first place.
Yeah.
Because if it is, then the process will succeed. A is symmetric positive definite if and only if this process succeeds.
Yeah.
Makes it all the way to the end without breaking down. Yeah.
Now, I understand the problem with dividing by 0. That's a really big one.
Yeah.
But is there a particular difficulty in going into complex numbers?
In that case, what you may have is, okay. Well, it would still mean that the matrix is not symmetric positive definite.
Yes, I understand that.
Yeah, so in that case, I actually in one of my students, Amber Summers, a co-author, her research, she is doing that. We are using a complex Cholesky factor. Okay. We prefer not to because we don't like to have complex arithmetic. But yeah, so if you're fine with that, then yeah, go for it. Okay. I'll assume it's still recording. Okay. All right. I need to remember, like,
You're not gonna know my password.
no, I mean to touch the mouse pad now and then. Okay. All right. Still going.
randomly say wiggle.
Okay. Now, the 3-2 entry. So we go across the third row down the second column, so that's going to be G31, G21 plus G32, G22. And we know everything on the right side except for G32, so we can solve for it. So we have G32 is, how am I doing on time? Okay. So that's going to be A32. So before, it's like this, except we have to subtract something off first. So it'd be minus G31, G21, which we know, we got it up here, over G22, which is guaranteed to be positive by the definition of Cholesky factorization, so there's no problem with that division there. And finally, A33 is a sum of squares. If we go across the third row, down the third column, and we get
1, 3, 2, 3, 3, all squared.
yeah, 3-1 squared, 3-2 squared, G33 squared, and we know everything except G33. So it's going to be like this. We take square roots A33, subtract off the other squares, and there we have our Cholesky factor, and that's it. So what you can see, this example is just big enough to show you that the formulas will get more and more complex. We're subtracting off more and more terms each time as we go from one column to the next. And that's why it takes still a cubic number of operations. So this is used to eventually derive the full algorithm for Cholesky factorization, which I won't give here, but it is in the book. And that pseudocode is what you'll use to write your own Cholesky function. Now, MATLAB has a Cholesky function, Chol, C-H-O-L, but it does something a little different. Instead of returning G as a GG transpose, it returns an upper triangular matrix, so it's A is equal to R transpose R. So different books do it differently. For some reason, I just went with this one. Okay, so now, any questions about this process, about how we solve for all the entries of G?
How are you getting the end result? How are you getting that? Like, I get all the way up until the last part.
Oh, here?
Yes. How are you getting the end numbers?
Oh, here I'm taking this equation,
Okay.
and I'm finding out which thing in here do I not already have from prior formulas,
Okay.
and I isolate it. So like here, G31 I got earlier, G32 I got earlier, so now I have to isolate that because that's the one I don't know.
Okay.
So what happens is, as you write out the entries, as long as you go like column by column and write out what the product is equal to, there'll always be exactly one thing you don't know. And that's what you solve for. And there's a 4x4 example of this in the book. So once you have the Cholesky factorization, as far as solving Ax equals B, it's quite similar to what happens with the LU factorization. So if A is SPD. So first, A is equal to GG transpose. So this is your Cholesky factorization. Actually, my advisor Gene Golub's computer in his office was cholesky.stanford.edu. And then you perform, just like with LU factorization, what's the next step? Forward substitution. So you solve gy is equal to b, and then you use back substitution with G transpose. and that's it. So the main work is done here. 1/3 n cubed flops, whereas the other steps require only order n squared. Actually, it's exactly n squared for both, and that's it. So, okay. Why do we care about symmetric positive definite matrices? They actually come up in a lot of applications. For instance, with differential equations, certain matrices we deal with there, and we will see later in the semester are SPD. There are other methods besides this one that are devoted solely to SPD systems. So, there's a lot of work done there that just makes that assumption because it's still relevant. Okay, so, all right, so, and the main relevance that I personally deal with is solving actually PDEs, partial differential equations, like those that are taught currently in Math 417. Okay, but there are definitely others besides this. This is one I deal with myself. Okay, so, all right, so to see how well you've been paying attention, given that prior to today, we already had a method for solving AX equals B for any kind of invertible matrix. So why did we bother for this one case of symmetric and or SPD matrices? What is the benefit of going to the trouble of developing these other factorizations? What do we get out of that? Yes, so specifically, efficiency.
1/3, 1/3, we cut it in half.
Yes, we cut the work in half. So that's one thing. Also, if we talk about just SPD matrices, what else did we gain? I guess you could call it convenience. What's one thing you don't have to worry about with SPD matrices that you do have to worry about in general? And it's still written on the board.
It's the lower triangle. Square root 3. Leading principles of matrices.
I love that.
I'm not dividing by 0.
Right.
They're all positive
The
numbers.
determinant's not 0.
Okay, so
But it is 0.
okay, so because those determinants of those minors are non-zero, LU decomposition exists. Therefore, what do you not have to do?
You don't have to pivot.
Pivoting. Yes.
So,
And I admit I did not write that on the board,
yeah.
and I really should. So we'll do some editing of your notes. But what I'm hoping is that I'm encouraging, making it possible for you guys to have better organized notes by organizing my own writing in the way that I have. So no, yeah, so I said this, but I should have written it. No pivoting required. So, okay. Even though it could still be a good idea, but not necessary. Yes.
But don't we also have a problem with Gaussian elimination is fundamentally unstable? And avoiding Gaussian elimination, and Gaussian elimination is a wonderful analytic method, but ultimately it poses a lot of threats in a numeric method. Am I missing the point here?
Okay. Technically, that concern is still there.
Yeah.
So yeah, and actually the matrices, the SPT matrices I mentioned for PDEs, they are, they can be ill conditioned. But the Gaussian elimination is a funny thing that it can be so awful in certain cases, but generally seems to work well. And I guess it's because of that people still go with it. But we are about to move on to other kinds of methods, like iterative methods. But
essentially, I'm wrong in saying avoid Gaussian when possible.
Because that's still a good idea to pivot if you can, and then symmetric pivoting if it's symmetric. And for a lot of symmetric positive definite systems of interest, one would use iterative methods instead anyway. And because there's there's really no assurance of robustness just because a matrix is SPD. It could be just as awful as any other. So yeah, so it's still a good thing to keep that in mind. Yeah.
Yeah.
Okay. That's the end of direct methods for AX equals B. And tomorrow, or no,
Next
Thursday. We do not have class on Tuesday because of a Mardi Gras break, which I'm very grateful for, as are you, I'm sure. In fact, I'm probably just as grateful as you, believe it or not. And then iterative methods next time. Okay, and